Okay, so the last thing on our list of major course learning objectives is something that has become kind of the standard for writing programming. Actually, we've been using it the entire semester. It's so common, and that's object-oriented programming. Python programming language only works in object-oriented programming. We don't have raw primitive data. When we have an integer in Python, it is an actual integer. We can, we only start with strings. So we can say, with the string met, we had all those methods, the dot find, dot split, dot slice, dot replace, a whole bunch of them. But a string seems like our basic type of data. It's actually an object. We have a bunch of other things with it. We actually have that with integers and floating point numbers as well. We just can't see too many of them. But there's some common things like the absolute value of an integer. And you can pull up prime factorization in Python, a few other ones that are built in. You can check the documentation on them, but we almost never use them. Most of our math operations, things we do with numbers, take two numbers. So it's sort of a short list of things we would do with only one number. But it's there, it's object-oriented programming. That's the last thing on our major learning objectives is start introducing object-oriented programming. In the 200 level course, we dive into it a lot more, but it's very kind of the standard, the way most programs are written, to the point that most of our programming languages, at least all the ones at the top of the most popular programming languages, are solely object-oriented programming languages. And we can just kind of force them to behave like a procedural language. That's what we've been doing with Python all semester. So object-oriented programming. So usually we go ahead and say that word, but since I'm writing notes on a board, and well, you're all probably taking notes along in either your computer or on a piece of paper. An anagram here is nice. So we, unlike most things in IT, we do actually say that out. But for an anagram, I'm going to modify it slightly by throwing an S on the end. There's lots of things we could make the S stand for, but instead of OOP, if we throw that S on the end, then it's oops, which is a lot easier to say. A normal word. And I wanted to express that because, well, that's what I wrote when I filled out my notes. So at some point reading through my notes here, I say oops. That's the anagram for object-oriented programming. I had a number of professors on my way to school use that as well. That's a common way to just modify that anagram slightly. And if we wanted to, there's no shortage of words we could find that would make sense that start with an S, we could tack on the end of that. So to talk about this, I like to start with two pictures. One of them is not even an IT thing. The thing about object-oriented programming, the reason it's so nice is basically we can think like a human again. So have you all had a biology class? I believe it's required for high school, so you would have had some biology, right? Maybe not one at the college level. But hopefully you're familiar with categorization, how we categorize the forms of life. The tree of life, really. Drawn inverted as far as a tree. But up at the top, there's just that general category, life. And everything is some type of life form. I guess I could say life form instead of just life. So the overarching category that includes everything, which you might remember from biology class, there's three main sub-branches. We have bacteria, archaea, and eukarya. I think there's an E in there. Bacteria, archaea, and eukarya are the first three subcategories of life forms. And then we can keep going. So one of the types of bacteria, like maybe E. coli. That's a common one. And a whole lot of them. A bunch of archaea over in eukarya. One of the subclasses of that would be plants. And another branch over here, but really kind of splits off into two things. We'll have fish and mammals are a couple of the subclasses there. And a couple subclasses of mammals might be humans and elephants. Hopefully everybody's seen a picture like that in a biology class or in a book somewhere and kind of know roughly what I'm talking about. Our basic tree of life, a very simplified form. But for object-oriented programming, I like to start with this picture because this is how humans naturally categorize things. And I'm gonna jump ahead a little bit here and draw a diagram, a typical object-oriented programming diagram. Am I still on board? Yeah. So up at the top, we'll have some overarching thing that we'll just call object. And then we'll split that off into different subclasses. That has just the basic necessities of what it takes to run in a particular programming language. But we'll probably want something a little more detailed when we go to work with it. Depending on the software we're writing, maybe we'll have a car object. Or maybe we're doing something with geometry and we'll have a shape object that has the code for working with either cars or shapes. Or something about animals. I tend to alternate between those three. And back to animals this time. I did shapes last time, cars the time before that. So our in-class examples are going to be animals. So I'm going to keep going here. I guess we could split that, do another couple branches, because cars, we could get more specific. We could have like sports cars or minivans. And notice we're getting much more detailed as we progress down, just like in our biology categorizations. Our animal data, maybe we have like some lion data, something that represents a lion or a cat or a dog. And we can keep this trend going. A couple types of dogs are like a Chihuahua or something I know how to spell. Let me write beagle. I don't know why Chihuahua popped first in my mind. Like a beagle or a black lab. And we get more and more specific about what we have as we progress down. And I like to start with this picture because we know from the field of biology, this is how humans naturally categorize things. And when we work in object-oriented programming, and we go to diagram what we just did, we end up with that same sort of categorization organization. So it's much, much better for us. We get to think like a human again. And then there's some trends we can follow here. Hopefully the colors will show up here. Does anybody have any like colorblind issues? Colors that I should avoid using or anything? Okay, I think that means no. I hope that's not something I shouldn't ask. But I often like to color code things. And I'd hate to be up here color coding stuff if somebody can't see a certain color. To make sure I didn't need to throw any markers away. But like with this biology organization, if we pick one of these branches, maybe a human, that's not the only categorization of it. Because this thing here at the bottom of the tree, or the top of the tree if it's drawn the other way, the bottom as I drew it, that would also count as all the things above it. Like a human also counts as a mammal. It has all the traits that it means to be a mammal, and it just adds more to that. What are the traits for mammals? Has hair, milk, warm-blooded, the basic things it means to be a mammal. And then a human adds more to that. The bipedalism, all the little details that separate humans from other mammals. So a human could also be counted as just a mammal in general. Or we could keep going up our tree. A human also just counts as a eukarya. Or a human could also just be a life form in general. And we'll have the same thing with our object-oriented things. Right down here, a beagle. Well, if we put together a bunch of data and methods about this beagle object, storing some data and the methods we need to work with it, well, that could also count as just the more generic data of what it means to be a dog, which is just more specific. So it could also count as our data form of what it means to be an animal, which is our general data type of an object for the language itself. So there's multiple ways we can view the tree. Any categorization we put on it can also go back up the tree. That will be important in a minute, because in object-oriented programming, we use a really big technical term that seems like a lot to express that concept. And I like to start here because it shows that one of the biggest advantages of it from biology. This is how we categorize things in biology, because this is how humans naturally categorize things. So we get to think like a programmer. We get to think like a human again when we write our programs. I'm gonna go ahead and erase these pictures and start putting in the more technical stuff about object-oriented programming. Is that okay? If I erase. We will see more pictures like this. I just wanted to jump ahead and start there to help express that advantage of thinking like a human. We categorize our data as more like we would as a human in general. Okay, that blue marker doesn't erase very well. And I don't see a spray bottle in here. This was one back there. No, I don't seem to have the erase board cleaning spray bottle. Okay, that's how much I was going to color code. I'll make it a point not to use the blue marker again, though. So we get to think like a human again when developing our software. It's a really nice advantage. After some practice, it should come somewhat natural. It's very confusing at first, and a point that is often very confusing here to people at the beginning. I'm going to try stating it explicitly as we start out here. What we're making is a data type. An object is a type of data. Objects are types of data. And I'm going to underline that. Types of data. So when we categorize them, so categorize with things like ints. It doesn't correspond to our methods. An object is more like an integer. And that's what those people off at first. A lot of times they're trying to think of the next step up from, we built functions, so now the next step up from functions, but it's a step sideways. We're back to a type of data. So it's like an integer or a string or that technical term that we don't use, right? The character text data, like, which was showed up on a question in quizzes this semester. We're not going to really use it. Integers are strings. Like we saw in strings, we have all those methods that go with the string, built into the string. So that's kind of what our objects are. They're like integers or strings or booleans. Or floats. Or other types of data. It's not, it corresponds to those a lot more than it would say to functions or scripts or libraries or other things like that. That often confuses people, so I'm just starting out with that explicitly stated what we are creating. So the idea was thought up back in the early 60s. He wrote it up formally in 1962, so probably thought about it for a little while. Some Norwegian guy, I'm not even going to pretend like I can pronounce his name. I'm going to take a guess here that at some point in your life, everybody in here has heard Norwegian names before, right? Or seen Norwegian names spelled out. So I'm not even going to attempt to pronounce his name, but a Norwegian guy thought it up in the early 60s. Thing is, unlike one word that shows up a lot when we're learning programs, things like efficiency, optimization, looking for improvements, or those who move on to four-year school after this, you'll spend a lot of time looking at the big O function, which is measurements of efficiency. It's a numerical value that tells us how much efficiency decreases as input increases. How do those things correspond to each other? Does tripling the amount of inputs take the exact same amount of processing on the computer? Does tripling the amount of inputs end up taking 10 times as much processing as the original value? That's a big thing to study in computer science for those maybe not afterwards. But those words show up. Object-oriented doesn't apply to that necessarily. There's a lot of inefficiencies and overheads, but it's better for the human. Like way, way better for the human. Just to make up a couple numbers here, think of it like this way. If the programmer can do 1,000 times more, right? Think about it mathematically. The programmer can do 1,000 times more, so plus 1,000 at a 10% loss in efficiency, minus 0.1, we're up to plus 999.9. So it's worth it because the programmer can do so much more. We're willing to give up that loss in efficiency and not make that a big concern because the human can do so much more with it. And I just made up those numbers, so I'm just going to erase that. Made those up to make that point, but the programmer can do more, but we do lose some efficiency. So in the 1960s, when he invented that, most of our computers couldn't handle it. But by about the mid-1980s, 1985 or so, what we would call the average computer could handle those inefficiencies and overheads that come with Ever pull up the list of in here for when Python runs? I think I did. The stack trace, whenever we can get to it from our debugger. And usually when I pull it up in class, it would have been near the beginning. It showed a long list of folders and Python scripts. We started expanding folders, and we can see thousands of things there running. It's huge, huge list. We wouldn't even have scrolled all the way through it. We wouldn't even have expanded all the folders full of scripts that have to run for a simple thing like add 2 plus 2. So there's a lot of overhead and inefficiencies involved with it. But the human programmer can do so much more that it's worth it. So it involves 3 key concepts. We're going to talk about each one in turn. Encapsulation, which the summary on that is everything that's needed is included. Those pictures were already erased. I drew everything in a little bubble. Everything that it means to be that type of data is included in that bubble. Inheritance, we'll do that like the tree of life comparison. And just like the way the tree of life goes on, we start with the life form in general, and then from that bacteria, archaea, and eukarya inherit everything it means to be a life form. But then they add stuff to it. Bacteria add a cell wall and a nucleus to every cell, and then eukarya then expands to more defined versions where we get to multicellular life, and then that expands to more refined versions like fish and mammals, and then all those details get added in. Things are inherited from the more generalized form of that in object-oriented as well. And the third key concept is polymorphism. An object can act like a different object, can behave as a different object. And that's that arrow I drew on there. I already erased it, but the blue marks left here on the board, where the blue arrows went back upwards. On our tree of life, just the biology one, we haven't started talking about objects too technically yet. On the tree of life, a human can also just be counted as a mammal in general. That's polymorphism. It can behave as more than one thing. And it always goes that way. The things that inherited from it can always behave as that. That's how we would use that. Or a human could just be considered a life form, the most general one, by polymorphism. It's polymorphic to it. So we'll apply that concept, and the big technical term shows up for that. Objects are going to follow something called the open-close principle. Once we create them, they're open for extension, which is inheritance. We can create a new object that inherits from that other one, but it's closed for modification, and that's encapsulation. The word capsule shows up in there. So you can think of it like a capsule. We put everything we need there and then seal it up. And other stuff can inherit from it, but we don't modify the original. We inherit from that nice sealed up version and add more details to it. So that's our first of the 3 concepts to look at. Encapsulation. And right there in the middle of the word, you can see capsule. So you think of things like a time capsule. Okay. That's a common one. If we put a time capsule together today, a time capsule is just a sealed up box that holds representations of what it means to be 2021. So if we put one together, we probably have a mask in there, some sort of computer or reference to a computer, newspaper clippings, if you can still find those, or magazines, but most everything's online anymore. That might make more sense if we go back to like a 1950s time capsule. If we dug up a time capsule from 1950, we would see what it would mean to be alive in 1950, sealed up in that box. Newspaper clippings and photographs and maybe some clothes to represent the style. And everything that it would mean to be alive at that day and time is sealed up in that time capsule. And encapsulation follows the same thing. Computers are a good example of encapsulation. As we start off here, most of the people who use computers have no idea how it actually works, right? Probably don't even care. They just know that it works. The workings are encapsulated inside the machine. And here on my laptop, everything's closed up in that nice little case. And I open it up and it works. Came that way off the store, I didn't have to put that together. Don't even really have to worry about how it works. Oh, if you're learning IT, so probably know quite a bit more than the average user about how computers work. What's an example on here? Do you know how the key presses work? There's a mechanical button here. And if we push, say, the G button, the letter G shows up on the screen, or maybe something else happens. If that key press is bound to a different event in the software. But there's a lot of things encapsulated there that work together. So computers make a good example of encapsulation. I like the donut picture to represent this. So I'll draw two circles here. And it's like layers of things. In the inner circle, we have our properties. Or our technical term is going to be attributes. But the properties, the data itself, the stuff we're storing, essentially our variables. Our term when we go putting this together is going to be data field instead of variable. And for those who have had a database class, it is not a coincidence that we use the same term there. But that's something that will show up near the end of the 200 level class after we talk lots and lots about object-oriented programming stuff. But it is not a coincidence that we rename our variables or the attributes for an object data fields, the same thing we call them in a relational database. And then the outer circle is behaviors. How it acts. Or our technical term, we want to call it methods. So we have attributes, which is our data, and the methods, which we've already seen methods. We usually use the words methods and functions interchangeably. The technical definition distinction between them is a method is attached to an object. That's an object-oriented term. But we pretty much all do object-oriented programming anymore. And ideally, somewhere off to the side is a client accessing that. There's some sort of client object, which is its own sort of object with that inner circle of attributes or properties about it, things that describe it, and an outer circle of behaviors. One of those would be the ability to access our object. Or at the intro level, if it helps, think about it, the client is the user that wants to actually use this object we're putting together. But it can't get all the way to the inner circle. And this is something our textbook kind of dropped the ball on. The object-oriented section in here is really thorough and everything, but the syntax they use is kind of considered bad form. So when we look at the examples in class, we'll talk about the better form, where we have this inner circle. Because in Python, we don't really have this protection layer. Outside clients can access our behaviors, and then the behaviors can access the properties.
You said last Wednesday that you'd have these assignments due maybe a bit later.
Oh, yes, I'm gonna push back the date on this.
All right.
It's not past due yet, is it?
No, I'm just like trying to start on the exercises and the assignment, and I'm just having trouble seeing where to even like start.
Okay, yes, at this point, anything that's still open, I will push it back to like the last day of the semester.
All right.
So you probably want to do them before taking the final exam, which will open on Wednesday. But you have, it'll stay open until the last minute of the semester. Just because there's questions on it, but they're multiple choice questions, so they're gonna relate to the lecture and the stuff. But yes, I will push back the date on the assignments for this. So it gives us a layer of protection, which we don't really have in Python. So it's there's a standard way that we simulate that layer of protection. If we were in the C family of languages, we can actually say things are private, and then they're not accessible from the outside, period. They're only accessible through the text file. And once they're in the compiled version, they're locked and sealed. But we don't really have that in Python. So programmers have kind of settled on a standard that we use. There's something about the programming language we can use that when we see it in somebody else's Python code, we know to treat that variable like it's private. But we don't really have the inner circle here. We will see that, and our book kind of skimmed over that altogether. And referring back to the computer example, like I said, that's a good example of encapsulation. Everything it means to be a computer is enclosed there. There's a behavior of pushing a button. And then that behavior that we can access from the outside, we're the client reaching in and accessing the button pushing behavior. And then that button pushing behavior can reach into the computer, the software, and access the attributes, the actual data involved that it relates to. And the basic idea for encapsulation takes a little bit of practice to get really used to putting them together. But everything that needs, every behavior and property the object needs should be included or built into it from the beginning. And that way it's ready for anything the client might ask of. I made a note here about another analogy that a lot of people find very useful. I don't find this other analogy very useful, but I've heard some people do. All of us think differently, so I wanted to make sure and share it with you in case this fits better with the way your brain works. And that's to use the analogy of language, like our regular spoken language, only a little bit different. In that case, the object is like the noun, and then instead of having properties that would describe that noun, the adjectives and adverbs and all that, separate from it, they are all included. So anytime we use that noun, there's like that inclusive list. We can't use just any word from the English language. There's just that small list that goes specifically with that noun. And same thing with the verbs or behaviors, the things that noun can do when we put it into a sentence. They're already included. We can't use just any external one. We can only use the ones built into it. I wanted to mention that analogy because some people find that helpful. I never really found that one super helpful, but all of us think differently. So you always think of it. We're talking about electricity. And the only actual experience we have with electricity is like maybe rubbing the feet on the carpet, touching the doorknob, which doesn't help at all when we're trying to visualize what to do with programming. So I like to refer to analogies as much as I can. So that's the idea of encapsulation. How much room do I have? What I got? A little more room. I'm going to move this over closer. I'll move the client over a little closer. That way that button's not so far away. So our client, in an ideal situation, which we don't have in Python, but the general way we can simulate it in Python, our outside client can access the behavior And then the behavior has access to the attributes, which is the data itself that we're storing. Some conceptual stuff, and even when we see it in examples, it takes a while to get used to really formulating these definitions into place and making sense of them. So just kind of introducing them, all these words and stuff here, because, well, it's a classroom setting, so obviously you're going to have to answer some questions about it on quizzes and stuff, technical terms. Our second main property is inheritance. And we can extend this encapsulated object. And everything, all these attributes and methods, or in more normal English, less technical terms, maybe better to think about it at the introduction level, these properties about it, the things that describe it, and the behavior, the things it can do, that can be inherited. It's a lot like we use the word inheritance in our normal American culture, right? People born, grow up, get a job, start a family, over a lifetime of working in a career, they build up some sort of savings and get a house and money and savings and all of that stuff, and it just accumulates over a lifetime. And eventually they'll pass away, and their children will inherit all of that stuff and then add to it what they accumulate over their lifetime. So sort of the same concept there, and it just builds up. We don't, it's like we don't have to start from scratch. This one will make a lot more sense when we see it in application. This one will make much more sense seeing it actually in practice. So this is kind of what we're going to pick up on here. The biggest thing we want to practice at this level is just encapsulating our object. Trying to follow that concept of everything that needs to be part of this object, everything that we would use to describe it, and everything that it can do is already built in. Like we saw with strings, right? There was that huge list of things that a string that we could do with strings. The dot find methods, dot replace, dot center, dot split. That big list we already saw, and probably didn't even get all the way through on the homework here because that list was huge and we had a very finite amount of time to do the homework here. But that's the idea with strings. So we're going to kind of simulate that with our own type of data. So what I want to put here is just some terms. Because there's more than one term we use for this. So we might say, call something a base class. And we'll talk about the word class here in a moment. And to go with that, there is the word derived class. If I can spell it correctly, our derived class will inherit everything from the base class. Another common way to describe it is the word super and sub. So our subclass is going to inherit everything from the superclass and then add to it in most situations. In some situations, it's just a renaming thing. We just grab all that stuff from from the bigger object, the super object, and give it a different name that is more meaningful in our software. But it still behaves exactly the same. And I almost said the third term before writing it up here. We also have used the parent and child terminology, which is nice. A child class will inherit from the parent class. It's everything it means to be that. So just like in our normal American culture, the child starts by inheriting the parent's name, everything it needs to be part of that family, right? And then children learn to speak and act by watching their parents. So then they pick up the behaviors and accents and everything from their parents. Then eventually that more direct use of inheritance, as parents grow old, the children will inherit their life savings and build on it, add to it, expand it. So all three of them kind of mean the same thing. And notice I said three, even though there's 6 words here, because they do come in pairs. We could say parent class or child class, or we could say base class and derived class, and it would mean the same thing. But what we don't want to do is mix our terms. We wouldn't want to say parent class and derived class, because that pair doesn't go together. So they do come in pairs. But all 3 pairs are kind of used interchangeably. I'll try to make it a point to use all 3 of them too when we get to examples. So we'll talk about this a little bit more. This one will make more sense when we see it in examples than this. This one comes with experience, but this is our starting point. So this is what we're mostly worried about at the intro level, the encapsulation. The inheritance will make a lot more sense with an example. Polymorphism, we'll look at that with our examples as well. That's the third concept. Still on the board, yeah. So number 3 is polymorphism. And we have a couple obvious ones. The way we most often use polymorphism relates to inheritance. The child class will inherit everything it means to be a parent class. So it's going to have all those same behaviors and same properties as its parent. So it can directly act like its parent. In strictly typed languages, that's important. Because when we set up our program, we have to say what type of data we're passing in. And objects are data types. So we'll say what type of object it is. But when we go initially write that, we might not know what the final object that's going to be passed in is. It might not even be created till almost runtime. It could be 5 chains of inheritance down from where we're currently at when we put methods together. And in that case, we can use something higher up that tree of inheritance, use the parent class, and then when it comes time, the programmer that's going to call the method we wrote can pass in any child or subsequent generation of child of that parent, and we know it's going to work with our method because they would have inherited everything it means to be that original one we wrote it with. But again, those 2 will make more sense in examples. The encapsulation is the one that kind of requires more experience. Some do animal objects. I guess now it's time to start talking about Python stuff explicitly. Then we'll talk about what the class in a moment. What we build are classes. I want to talk about classes first, and then we'll go to the Python explicit stuff. So I already used it. The term is class. And what it is a blueprint or a design for an object. Is it okay if I start erasing stitches on the board here? This has been up here for a minute. This is a new thought because this has confused people before. We are making something more like an integer than a method, than a function. It's not the next step up from where we were. That's something that often confuses people at the intro level, I think. So class. This is what we're actually going to make. And what it is a design or a blueprint for an object. A design or a blueprint. For an object. So we don't necessarily create all our objects at the final time. We just create, we set up what it means to be that type of data. And we'll create instances of an object. So going back to the analogy thing, a really good one to use in America is subdivisions. That word blueprint, right? I think everybody in here has seen a subdivision. Typical American subdivision. Extreme case, the entire subdivision of 2-bedroom ranch homes with a garage and a basement. I guess that's like Whittier, city in LA. You've at least seen it in movies or TV shows. Oh, the classic show Wonder Years. That's been making a comeback. That was filmed in Whittier. 120 square miles of 2-bedroom ranch homes. It's a huge chunk of LA built in the 50s. But that just mile after mile after mile of ranch house after ranch after ranch house. They're all built from the same blueprint, right? There's that initial blueprint of what it means to be a 2-bedroom ranch home with a garage and a basement. And those around here as well. There's several of those near Sellersburg, kind of going into old farms. They build a road going back into what used to be a field for a farm and set up a bunch of 2-bedroom ranch homes around it with a garage and a basement. And that's what our basic blueprint is. That's what we design. But then when they go and get built, a particular instance of a 2-bedroom ranch home with a garage and a basement, they're all a little bit different, right? Some of them have the garage on the left, some of them have the garage on the right. Some of them have a full basement, some of them have a half basement. Some of them have square windows in the doors, some of them have round windows in the doors. Different porch decor. The little subtle details work in later. But there's that overall blueprint or design of what it means to be that thing. A 2-bedroom ranch home or an object for object-oriented programming, that initial design. Going back to other data types, there's that core design of what it means to be an integer, or that core design of what it means to be a string. We can add stuff to it, and for our particular needs, we can add some more functions that a string could do. But there's still that core design. If we add stuff to it, we inherit all that initial stuff and add more to it. And that's what a class is, a blueprint for our object. And we use UML, I'll write up the UML representation. I'm going to leave the encapsulation picture because I might point at that. Again, it's okay if I erase inheritance. See, I had not here in class. It's been up here for a minute, so hopefully just some terminology. And you've probably heard those words before. If you've been studying IT stuff for more than a week, you've probably heard words like super and sub, parent and child. Base and derived isn't used as much as it has been in the past, but it's still around. So we talked about unified modeling language, at least briefly. IT, our modern world, is a global world, all interconnected. And in IT, there is an international standard of communication. Since we all speak different languages, it's a pictorial thing. Some people really like to just say it's like hieroglyphics. Right? Instead of these arbitrary symbols that represent sounds, we use pictures. Because then it doesn't matter what language we speak, we're looking at a picture. So our UML symbol for a diagram is like a rectangle. And up at the top is an identifier. Then we'll list out all of the attributes or properties. I'm going to write the technical term here. And then a line, and we want plus and minus signs to represent public or private. That's the donut picture here. It says it's like a layer of protection that the outsiders can reach the behaviors and that the behaviors can reach the attributes or reach the properties. But maybe we want things fully accessible from the outside, which we have in Python. After I talk about the technicality that our book skimmed over, that's how we're going to write our code here because it's so much easier. It's what most people do. I just want to make sure you're aware of that technicality. The same thing down here, we'll have either public or private behaviors or methods. Because not all of our methods need to be accessible from the outside. There's a lot of things that are going to be completely internal methods that don't need access from elsewhere. So we want to specify whether they're public or private. So that's what our UML class diagrams look like. There might be an assignment about drawing some of those in here. I think it got removed from the current course shell. You will see it at some point. Unlike some of our UML diagrams, generating this does not take any thought whatsoever. Thought is needed to organize that on a page and make it look nice and easy to follow, because we'll typically have lots of objects. But most of our IDEs and other software in general can just look at a script or a program and generate the UML class diagrams. And then all the human is needed for is to organize it nicely on a page. The computer can't organize it nicely. Computers can't really process visual stuff yet. I think there's been some progress for that, but things like organizing it in a way that makes sense is still a little beyond that. Something would have to be able to pass the Turing test. Right? The standard check, which is essentially what the Among Us game is. If y'all weren't familiar with that, you probably heard the thing, Turing test referred to a number of times. The game Among Us is an outgrowth of the Turing test, where you have to choose which one of the people playing the game is lying. The original test was a party game where two people would go hide, a man and a woman, and then the player could look at their written responses, would ask questions, and could look at the written responses. And one of them was lying, and the other one was telling the truth. And from looking at those responses, knowing that one's lying and knowing that one's telling the truth, figure out which one's male and which one's female. That's what the Turing test is. So if you've ever played the game Among Us, you have taken the Turing test and probably done quite well at it. So computer players in that game do terrible. But it doesn't take any thought at all to do this. Things that can pass the Turing test are just needed to organize that nicely on a page so somebody else can make sense of it. But this is what our diagrams look like, and then we'll have multiple ones. So something that will inherit from that. We'll have one over here, maybe a chain of things over here. And something that confused me for the longest amount of time, or really big here, and carefully, because we have different types of arrows. We'll just do these basic ones. This would be the child that inherits everything, and we represent that by the arrow pointing up to the parent. And that confused me for the longest amount of time. But what it is that arrow points with polymorphism. So inheritance flows like backwards down the arrow. So this child, or this child, will inherit everything it means to be the parent object, and then add some stuff to it, and then flowing backwards down the arrows again, we get another child object, a child of this parent, that will inherit everything it means to be the original, plus what this added to it, then add a little bit more. And it confused me for the longest time because I always thought the arrows were pointing the wrong way, but the arrows are pointing with polymorphism. So this child inherited everything in the chain above it. So this child is perfectly capable of acting like this object. If this object is the one that we need, but maybe the syntax is a little bit better in this and this one, we can use this one. And we have all those methods we originally need from the parent. The next picture I want to draw is this explicitly for, or start talking about this stuff in Python. The one we're going to actually use here. And then we have an example, which I'm thinking we'll probably do the example on Wednesday. That way we don't run really late tonight. We're getting near the end of the semester, so I assume you all have some work to do. So I want to make sure there's plenty of lab time to get the work done and do this stuff. So we'll get through the conceptual stuff here and then start into our example on Wednesday. So we can do it nice and slow and detailed and try to make sense of all that. And correct the point in the book that the book did that is generally considered very bad form. But after going over that technical direction, we're going to write everything that same way. Really, I just want to point out that it is bad form and to at least be aware of the proper way to do it. Any questions about the concepts so far? These are all generalized. So I want to talk about some Python stuff here that we're going to use when we get to our examples. Okay, I assume the silence means no questions. It's okay if I erase this first section over here. So what a class is, that's what we actually make. We'll open up a text editor and put together something with the .py file extension, and it's going to be the design for an object. And then in another Python script, we will instantiate an instance of that class, and that's what we call an object. So some terminology. So in Python, the language we're actually going to be working in this semester, or for the next week, we're almost done with the semester. There is this object up at the top that is actually called object. Oh, whoops. In Python, it has a lowercase o. And that's common in a lot of our languages. And most of them, it's spelled with an uppercase O. If we go with the parent-child terminology, we could think of this as the grandfather. Or ancestor, or grandmother. Yeah, I should write that. Better for nature, right? Males aren't really necessary. If you all haven't kept up on the latest, haven't heard, it just happened last month, but politicians get so much of the news coverage. But even though the world's full of more interesting things, but they found a couple more bird species that can change their gender if there's not any males around. Females can become males almost at will if there's not enough males around the females. And it's a bird species now. So it's a couple more species that I guess that first showed up in the Jurassic Park movies. It's been known about for a long time, but it shows up more and more and more. And kind of the feminine side is probably more important for, or fits that is not better as an analogy. If we use the parent-child terminology, the grandmother, the ancestor of every object we will make, and every object that exists in Python, the stuff that's already there, the integers, the ints, the strings, the floats, the booleans. What else have we used? The TK stuff. We just used a whole bunch of that. All of those things that are there, and more that aren't officially there, because GitHub is full of objects. That's what a lot of it is on GitHub. It's open source code, objects people put together that are useful, They didn't get accepted into the official version of the language, but they're still useful, so they might as well share them with people. No need for everybody to start from scratch every time, is the concept. And that's why programming has grown so much since object-oriented programming took over. The idea was around for a long time, and it was still just sort of creeping along progression. There was steady improvement. But then about 1985 or so, machines could handle the excess overhead and inefficiencies. And object-oriented programming took off, and it's just completely took over after that. So we're going so slow on the description. So there's this object thing, and I'll draw the inheritance arrow. And then down here, I'm just going to put dot, dot, dot. And this is everything in Python. Everything else in Python. It all inherits from the object. So the behaviors of what it means to be an object in the Python programming language. Everything has those. So we're going to look at a couple of them. Not an all-inclusive list. There's 3 that we want to start with. I'm going to make a list of 4. And the reason why is the first one. So one thing, everything that gets inherited from that, the names start with 2 underscores. So first one is underscore underscore new, underscore underscore, and then it's a method. So parentheses, and I'm just going to put dot, dot, dot. We're going to pass stuff in. And like I just said, there's 3 that we're going to use this semester. I'm going to make a list of 4 so I can grab the red pen here and draw a big circle around this. And do standard no symbol. At this level, that's just a strict no. We don't want to mess with this. At a more advanced level, we know lots and lots of stuff about that. We know assembly language and machine language. I work with all that. It is still a really, really bad idea. Like Python is the most popular programming language in the world. They have their choice of programmers in the world to develop the language itself. They knew what they were doing. We can trust what they did with the new method. So even when you know a bunch of stuff, it's a really, really bad idea. So I just wanted to put that on the list for the no symbol, right? We can access it, but that common thing that shows up in the English language, right? Can and should are 2 entirely different things. We can lower our heads and run full speed into a brick wall. That does not mean we should do that. And you would probably be better off doing that than messing with the new method. If you do that, you have to start changing your interpreter. So even though we have access, avoid that one. Ones we will use, underscore, underscore init, INIT, short for initialize, underscore, underscore, and then there's parameters we will set up to be filled later. This is our initialize. We have to use this one every time. We can't create a new object without using this. So whenever we go to assign something, the Python interpreter is automatically going to call the init method. That's how it sets up a new one. And when we ask for a new object, oh, we just saw the TK, right? So when we imported it, we said GUI equals this TK object with parentheses. We call that a constructor. So in some of our other languages, the init is the constructor. That's how we make a new one from the blueprint. Oh, which is actually a good terminology for an analogy. We have the blueprint, and then we construct something from that blueprint. So this is our constructor. We can't make an object without it. So we'll use that every time. A couple others that we're often going to want to use. Underscore, underscore, str. Again, all of these, everything we inherit from object has two underscores at the beginning and end. And str. So a method that I know all of you all have called many times this semester and sent error messages when you forgot to call it is like when we go to print an integer. If we say print and then throw an integer in that spot or a variable holding an integer, we get that type error. Right? And we cannot concatenate string and then and so we have to wrap it in that method str. We wrap it around this other method built into the language called str. And all this right here does is it calls this string method that everything in Python inherits from object. So we usually want to do this because we want to say what it means to be a string. So most recently, the last two times, the examples I have the three that I cycle through. So the last time was shapes, and the time before that was cars. So I'm making animals. So we're going to do an animal object. So we'll inherit a bunch of things, and our animals are going to have names and ages and make sounds. So when we get down to like the dog object, we'll have the class, the blueprint, the design for it, and what it means to be dogged at it in whatever that example software we put together is. We probably want to use this string method because we may want to print stuff. And in that case, it's always unique. For that example, what is like, maybe once we go to use it, we'll have a dog named Fido is the particular instance. But what does it mean to be a dog object number? Or what is it going to mean to be a cat object for the animal examples? Or shape examples. What does it mean to be a shape in general? Or what does it mean to be a triangle as opposed to be a square? We might want to print that out at some point. And to do that, we override the built-in string method because the default version prints out a spot in memory. You've probably seen the default version printed out. And like if you try to make a function call and forget to print out the parentheses, then you just get it prints out what spot that is stored at in the RAM. That's the default version. We probably don't want that. We want something more explicit that looks nice, concatenated into a sentence to tell the user what our object is, what the object is. So we usually want to override that so that we can print stuff, put it on labels and things like that. And another one that's like string, again, it's going to start with two underscores. That's EQ. We usually want to do, that's going to be equals. And we'll pass some stuff in. Actually, that one we always have to pass in another object. So whenever we call equals, we have to pass in something else that inherited all this stuff from the grandmother object in Python. And this is where we define what it means for two things to be equal. We're going to use animal examples, probably start working through the example on Wednesday. But we'll have the generic animal, and then have like cat and dog, hyena, a couple different examples, gorilla, a few different things. When we get down to the dog examples, like what will it mean for two dog objects to be equal? We have a dog named Fido that's a 3-year-old beagle, and another dog named Sparky that's a 6-month-old pit bull or something. What would it mean for those to be equal? Because the default, the one that's inherited, is that it is stored at the same spot in RAM. So the only way if we don't override that, the only way we'll get equals. So if we need to set up a condition, like if object A equals object B, The only way we'll get equality is if they are stored at the same spot in RAM. So we usually want to override that. And those three are consistent across most of our languages, pretty much all of them. We always, any object-oriented languages, we will want to set up some sort of constructor, some sort of string method. The syntax obviously is different language to language. I wrote the Python syntax here because that's what we're looking at. And some sort of equal method to describe that comparison. What does it mean for our object to be equal to another? So like shapes. I did that last time. If we're doing some geometry software and we have shape objects representing, one of them represents, some of them represent triangles, some of them are circles, some are squares. What does it mean for them to be equal? Because there's probably more than just the same spot in memory that would count as equality. Maybe our concern is area. We don't care whether it's a circle or a triangle. If it has the same area, we're going to say they're equal. Or the same parameter. Those would be useful things in geometry. No matter what the shape is, we want to know what things have the same area. So we would just override that default method to define what it means to be equal. And one that we usually don't inherit, that most people like to include, and most of our languages, not just Python, we don't inherit it, but to go with it, equality is some sort of comparison, a compare to. Because usually we have multiple things we do with our selection structures, right? If something is equal to another thing, if it's bigger than something else, or if it's smaller than something else. So most people go ahead and add one more that is built from scratch. That's like a compare to. How does our object compare to another object? If we have two shapes, what does it mean for one of them to be bigger than the other? Are we counting the number of sides? Because like a triangle has 3 sides, a square has 4 sides, an octagon has 8 sides. So maybe we would just want to know how many. Say the bigger is the count of the number of sides, and which would make circles the biggest thing because that's approaching an infinite number of sides. One of the concepts of a circle, infinite number of points. There's not really a side to a circle. There's so many of them. Or maybe we want to compare the object strictly the area. Doesn't matter what shape it is. If one area is bigger than the other, then we're going to say that shape is larger than the other one to work into our selection structures. These three we will want to use pretty much every time. Avoid this one. If you start messing with that, you might have to go change your Python interpreter. But it's a programming language. It's open. We can do that. Probably not at the introduction level. So strictly avoid that now. And later, as you progress further, it's probably still a really good idea and kind of important to not mess with that. The people who put that together are really some of the world's best programmers. We can trust what they did when they put that together. We don't need to go change it. There are other ways to get the same result. But those three we'll want every time. We'll want to construct something from that blueprint or design we have. We'll want to override the string method, which in most of our languages is just actually the words toString. Convert that into a string, but something like that, something we can print it out. If we say print on our object, what words are going to show up for the user to look at, for the user to see? How do we describe our object? We always want to have that, because we're putting software together for a user for the most part. So we need a way to get that stuff back out. And if we don't override that, all it tells us is what spot it's stored in RAM. And that's stored dynamically, so that's going to modify. If we do run a few more instructions and check again, it might be in a different spot. And we usually want to override and describe what it means for our object to be equal to another object, because those two are completely dependent on the situation. We cannot say what it means to print an object until we know what object we're trying to print. Same thing with equality. We can't say what it means for two objects to be equal until we know what two objects we're trying to compare and find equality for. And then from here, that's the basic concepts for the introduction level of this. We'll reiterate these, say in slightly different ways, talk about some more stuff, but mostly work on examples on Wednesday. We're just going quickly. So looking at the syntax, seeing them applied, it takes a minute to get used to it. It's very different. But there'll be lots of practice. We introduce it here, and then the 200 level course is pretty much all working with objects. First 200 level course, here we'll look at encapsulation, and the first 200 level course looks at inheritance and polymorphism a little more. 200, 210, 220, 230. I think there's 240 there as well. And then the 250 level, 250 to and above, that's the next level where you look at things a little more detailed. And it gets more and more detailed. And those continuing on to a 4-year degree will continue on with more and more and more and more details about this. So you'll see lots of practice. Just introducing it here. It's going to seem very confusing. It is for everybody at first, and then it'll kind of start to make more sense. But one thing that'll help it make that doesn't help with the confusion at the introduction level is we get introduced in a classroom where we're under tight time constraints, and it really isn't going to make a whole lot of sense for you to do more and more stuff. Or video games are really useful for figuring it out. A whole lot of people agree that when you start putting together a video game with object-oriented programming, then it makes more sense because we're simulating the real world and see how the objects in the game correspond nicely to objects in the data. But we will start seeing that in examples on Wednesday. This is about an hour and 10 minutes for lab time this evening to start working on stuff. Got a week left. Next Monday is our last class tonight. So, anybody have any questions about these concepts on object-oriented stuff? And we will see it in examples. Encapsulation is still kind of hard to see an example. Inheritance and polymorphism will make a lot more sense. We'll see that on Wednesday, and it'll make more sense when we see it. This one is going to build up with experience. So maybe about halfway through you get 200 level class, the encapsulation stuff will start making more sense. Otherwise, that was it for this evening. I'll see you all on Wednesday, and we'll jump into an example, seeing this in examples. Y'all have a good night.
Thank you.
Thank you, Chris. You have a great one.